Third, normality and homogeneity of variance. It was not a problem to continue with our analysis of variance. However, suppose that our data had clearly violated the homogeneity of variance assumption, then what? Now let's have a look at 3 different scenarios. First, here we have nearly equally sized samples, but the largest standard deviation in the sample is larger than twice the smallest. I have now a pointer. So here we have the smallest standard deviation, which is 10, and the largest is 29. So obviously there's quite a big difference between the various standard deviations. But the samples are nearly equal, 20 or 19. Now, the homogeneity test in this case indicates a significant violation of the homogeneity assumption, and we should be cautious, and there are possible remedies like transforming our data, because a violation of the homogeneity assumption is often related to skewness of the distributions. Particularly if you have right-skewed distributions, you will often find that the variances tend to differ significantly. And skewness can be remedied by applying some sort of data transformation, which we will be looking at in Unit 4, fourth part of the course. Well, the fourth lecture. Another way of dealing with heterogeneity is by adjusting the significance level, making alpha somewhat smaller, because what we don't want is to increase the probability of a type 1 error. And if we have a violation of the homogeneity assumption, that's one of the problems that may occur, that the probability of a type 1 error is actually larger than the nominal level that we specify by the choice of our significance level. So what we can do in order to safeguard against inflation of the type 1 error probability is by setting the alpha level somewhat lower. So if we have a problem like what we've just seen, something like this, conspicuously large differences in the standard deviations and a significant Levene test, one of the things we may opt for is adjustment of our significance level, making it smaller. Then we can also choose for a more robust alternative to the conventional ANOVA F-test, and that's known as the so-called Welch-procedure. You may be familiar with the fact that if you do an independent samples t-test, you always have the opportunity to choose between a t-test where you assume equal population variances and an alternative where you do not make that particular assumption. So if you don't assume equal population variances, you can still make use of the independent samples t-test, but then you get a different sort of output. Now, this same alternative is also offered in the form of this so-called Welch-procedure. And then, finally, instead of doing an analysis of variance, you can choose for a so-called non-parametric test, known as the Kruskal-Wallis test. In this particular case, non-parametric tests focus on ordinal information in the data and do not make any specific assumptions on the form of the distribution or on the equality of variance or some such distributions. So if you do a non-parametric test, you don't have to worry about the assumption of equal population variances, but the price you pay for choosing a non-parametric test is that you lose a certain amount of statistical power because the non-parametric test ignores the quantitative information and only focuses on ordinal information. So these are things you can do if you're faced with a problem of heterogeneity of variance. Now, the Welch procedure is can be ordered in SPSS simply by clicking on Welch, as you see over there. Here we have the one-way ANOVA procedure within SPSS. We will be practicing that coming Wednesday. And as you can see, if you click on options, one of the options you have is to order a Welch test, which is the robust alternative to the ANOVA test. Okay, so here we see the output for the standard ANOVA for the data that I've just shown you. So the data where we have nearly equally sized groups, but we do have a significant violation of the homogeneity assumption. We can see the f-test is very significant. The p-value is 0.007. The robust Welch test gives, well, the same p-value, so it doesn't really make much of a difference whether we use the original ANOVA or the robust Welch test. It seems that the traditional ANOVA test is itself robust against violation of the homogeneity or variance assumption, and this has to do with the fact that we have nearly equally sized groups. If, on the other hand, you don't have nearly equally sized groups, then things may turn out a little different. Here we have, again, a situation where we have clearly different standard deviations. The smallest is 10, the largest 29. But in this particular case, you can see that the sample sizes are clearly different. The largest standard deviation is to be found in the largest sample. And that has certain repercussions. First of all, we can see that the Levine test indicates that there's a probable violation of the homogeneity assumption. And yes, we can see that the largest standard deviation is to be found in the largest group. This has the consequence that the mean square within the pooled estimate of the error variance is somewhat inflated, because the largest group indicates a relatively large standard deviation and thus a large variance. So the pooled estimate of the error variance is inflated by the fact that the largest group has a conspicuously large variation, a conspicuously large standard deviation. And in that particular case, we can see that the conventional ANOVA f-test will tend to be somewhat conservative. It becomes harder to reject the null hypothesis. Well, in this case, of course, the result is very clear-cut. P-value is still very small, 0.005, and we can see the robust Welch alternative delivers an even smaller p-value, and that's because the standard ANOVA test in this particular case, where we have a conspicuously large standard deviation in the largest group, in this case the ANOVA test tends to be conservative. Now here we have a third example, unequal group sizes yet again, and in this particular case we can see that the largest group has the smallest standard deviation. In this case, we have 38 observations in a group with a conspicuously small standard deviation. That means, of course, that the pooled estimate of the error variance tends to be deflated, and thereby the probability of type 1 error tends to be inflated. That means that the robust Welch test will return a somewhat larger p-value than the conventional ANOVA test. The ANOVA test risks of producing a significant result too often, and the robust test in this particular case is clearly superior. So there we have three different scenarios that we can be faced with if we have heterogeneity of variance. If we have equally sized groups, usually it's not much of a problem. If the largest group has the largest standard deviation, ANOVA tends to be somewhat conservative. That's not much of a problem either, except that we lose a little bit of power. And if we have the smallest standard deviation in the largest group, then ANOVA tends to be too liberal, and that's clearly something that we want to guard for instance, by choosing the Welch-procedure. Okay, we are now returning to our original example. We've seen that the normality test was no problem, and the normality assumption was no problem, and the homogeneity or variance test of variance assumption was no problem either. So we're going to perform a one-way ANOVA and order multiple pairwise comparisons as a follow-up. Now, clearly the ANOVA returns a significant result. It's smaller than 0.05, so it's likely that the population level, at least one of the population means, differs from the others, and that means that we have to do some follow-up research in order to pinpoint where the real differences probably are. Now, what we could do, of course, is to simply carry out all possible, that is in this case, say 6 pairwise comparisons, all against a significance level of 5%, but of course, in that case, we are faced with a multiple testing problem, because although we have first carried out an F-test, this F-test does not completely guard against the possibility of making type 1 errors in the follow-up pairwise comparisons. So what we can see is in this particular case, it says LSD, which means least significant difference, where we simply use a 5% significance level for each and every pairwise comparison. If we do that, we see that there's a significant difference over here, the second one over there, and the third one over there. So we have 3 significant differences, but we are faced with a potential multiple testing problem, which we really would like to guard for. We all probably know the Bonferroni correction. The Bonferroni correction simply divides the alpha level by the number of independent comparisons that we would like to make. And we are making 6 comparisons. So if we have a 5% significance level, we divide the 5% by 6, and we get a new significance level, which will guard against inflation of the type 1 error probability. So if you look at this particular column, here we have ordered Bonferroni, here we have the column with the p-values. In this particular column, all the original p-values are multiplied by 6. So instead of dividing alpha by 6, we can also, of course, multiply the p-values by 6 and compare the new p-values to the original alpha of 0.05. So exactly the same solution. As soon as the multiplication by 6 gives rise to a p-value larger than 1, then you will find the value 1 in this particular column. That's the reason why you see so many 1s over here. And we can see immediately that there's only one particular pairwise comparison that is now significant, and that's this particular one. The difference between the group which was faced with difficult labyrinths and was not primed, and the group which was faced with easy labyrinths and was primed. So the two most extreme different groups really differ significantly from each other. And here we have the 95% simultaneous confidence intervals. Now, obviously, the Bonferroni correction is somewhat well, it's a bit of an overcorrection, because by first doing the ANOVA test, we've already established that at least one of the population means will be different from the others. And that is to say that of the 6 pairwise comparisons that we're going to do as a follow-up, 3 of these should be significant, because we've already established that one of the groups has a different population mean. So all pairwise comparisons involving that particular group should give rise to a significant difference. So 3 of the 6 pairwise comparisons have already been controlled for because we've first carried out the ANOVA F-test. So we only have to correct, we only have to do a multiple testing correction by dividing the alpha level not by 6, but by the remaining 3 pairwise comparisons. The 3 pairwise comparisons that we haven't controlled for yet. Now we can do that by using, well, what we might call an adjusted version of the Bonferroni correction. You can do that manually by ordering LSD. Let me say that as by ordering the least significant difference. Sort of important misunderstandings. And set the significance level at 0.0167. This is, of course, 0.05 divided by 3. So we're now asking for a new significance level of 0.05 divided not by 6 as the ordinary Bonferroni correction would do, but divided by 3. Next, we have to. We simply have to. We have to. The p-values that are observed in this column have not been corrected, of course. These are simply the p-values that you would that you always get without any correction. So what we have to do is either multiply these particular p-values by 3 ourselves, or by comparing these p-values to our adjusted significance level of 0.0167. We can choose either method, doesn't matter. So you might ask, so if all you do is simply calculating a new p-value or a new significance level by hand, then what's the meaning of putting this particular value in this box over here? I mean, why do that at all? Well, that has to do with the fact that if you look at the last two columns, it now says 98.33% confidence levels. This means that these are actually 95% simultaneous confidence levels according to the adjusted Bonferroni correction. And so that means that after having applied the adjusted Bonferroni correction, the probability of finding a confidence interval in any of these rows that does not contain the true population mean, but really should contain it, so that you're making. Well, I'm talking a bit fuzzy now. Well, the idea is if you have a 95% confidence interval, normally, of course, the 95% confidence interval is applied to any interval separately. But if you do a Bonferroni correction, then the 95% confidence interval applies to the whole collection of pairwise comparisons. So that's a much better guard against making type 1 errors, of course. Now, by adjusting this particular significance level by dividing the alpha level by the number of pairwise comparisons that we haven't corrected for yet, so by doing the adjusted Bonferroni correction, we get, if we order the LSD, we get what we get effectively is a 95% simultaneous confidence interval according to the adjusted Bonferroni correction. So if you actually do the Bonferroni correction, you will, like we did earlier over here, then you get the 95% simultaneous confidence intervals, but these tend to be too large because we lose power because we are overcorrecting. And by manually doing a smaller correction, which we can designate as an adjusted Bonferroni correction, we're now getting simultaneous confidence in 95% simultaneous confidence interval, where the intervals are actually smaller than if you would order the ordinary Bonferroni correction. You will find, if you find this a bit confusing, then probably if you read the summary text, you will hopefully understand what I am trying to explain here. It's not a difficult idea, but okay. So in general, the best correction the best correction in terms of power and of type 1 error probability, if you only do pairwise comparisons, is a correction procedure which is known as Tukey's honestly significant difference, or HSD. The Tukey correction is only suitable for pairwise comparisons. It's based on a so-called student-type range statistic, and it rests on the assumption of homogeneous variances. So if the assumption of homogeneous variances is clearly violated, then you should not order the Tukey correction as a multiple testing correction. If, however, the variance assumption is not violated and you are only doing pairwise comparisons, then the Tukey correction, which can be ordered in the posthoc window over here, is mostly the best multiple testing correction that you could opt for. Okay, I'm leaving this behind now. We're running a bit late. The corrections for multiple testing obviously reduce the power of our test. We're making the alpha level somewhat smaller, and that means that the power of our test becomes smaller as well. What we could ask ourselves is, are these pairwise comparisons that we do as a follow-up procedure, are they really desirable, or are they even necessary? There is an alternative which is known as planned comparisons, or alternatively as contrast analyses. And these contrast analyses are based on more substantive questions that you would like to ask about your data. In this case, we have 4 particular groups, but what we actually, and we can, of course, after a significant F-test, do all sorts of pairwise comparisons, but that's a rather blind way of trying to find out where the differences actually are. A more meaningful way would be to try to directly answer the questions that we're actually interested in. For instance, the question, is there an effect of difficulty on squeeze time? Is there an effect of priming on squeeze time? And lastly, is there an interaction effect between difficulty and priming on squeeze time? Now, we had the following 4 groups. The first group had difficult labyrinths and a perseverance prime. The second group had also difficult labyrinths, but a neutral prime. And the third and fourth groups both had easy labyrinths, but were differently primed. Now, if I want to investigate the effect of difficulty, this means that what I actually want to do is to lump the 2 groups that receive the same labyrinth condition, either the 2 groups that received difficult labyrinths or the 2 groups that received easy labyrinths, to lump these together, to take the average of the 2 averages and compare these to each other. Is the average of the 2 difficult conditions equal to the average of the 2 equal conditions? So that's what I would want to investigate. Putting it somewhat differently, of course, this amounts to saying if I take 1/2 times mu1 plus 1/2 times mu2, does that equal 1/2 times mu3 plus 1/2 times mu4? Or, and this phrasing the null hypothesis, if I say 1/2 times mu1 plus 1/2 times mu2 minus 1/2 times mu3 minus 1/2 times mu4, does that equal 0? So this is exactly the same question as I phrased over there. If I look at the average of the first 2 mu, are these equal to the average of the last 2 mu values? So this is what we find in this last row. And if I multiply these coefficients, they are now 1/2, 1/2, and minus 1/2, and minus 1/2. If I multiply these coefficients by any constant, it does not change the hypothesis. So if I multiply these coefficients by 2, I get as the new coefficients plus 1 times mu1, plus 1 times mu2, minus 1 times mu3, minus 1 times mu4 equals 0. That's a null hypothesis that I could investigate, and that answers the question whether or not it makes any difference whether you've been faced with easy labyrinths or difficult labyrinths, or in other words, whether there is a difficulty effect. So here we have what is known as a contrast. In a contrast, you have coefficients applied to all the various population means, and these coefficients should sum to 0. In this case, you can see that they do. 1 plus 1, minus 1, minus 1. They sum to 0. And it's customary to designate a given contrast by its collection of contrast coefficients. And if possible, we will try to use value 1 in our contrast. So in this case, we have a contrast 1, 1, minus 1, minus 1. And if you know which groups these particular coefficients pertain to, you can immediately see for yourself what sort of an effect is actually tested here. Because I know that the first two groups both had difficult labyrinths, and the last two groups both had easy labyrinths. I can immediately see by looking at this particular collection of contrast coefficients that what I'm actually doing is testing for a difficulty effect. Now, of course, likewise, the contrast for testing the effect of priming would be plus 1, minus 1, plus 1, minus 1, because the first and the third groups, I believe, both had a perseverance prime, and the second and fourth groups both had a neutral prime. So by choosing these particular contrast coefficients, I'm actually comparing the two perseverance primed groups with the two neutrally primed groups. So here we have the new contrast, mu1 plus mu3 minus mu2 minus mu4 equals 0. Test of a priming effect. Now, the interaction effect can be simply constructed. If you want a contrast for an interaction effect, you can construct that by multiplying the corresponding contrast coefficients. So for the first group, we have for the difficulty prime plus 1, for the difficulty contrast plus 1, for the prime contrast also plus 1, so the product of these two is plus 1. For the second group, for the difficulty contrast we had plus 1, for the priming contrast we had minus 1, the product of course is minus 1. For the third group, the product is minus 1, and for the fourth group, the product of minus 1 times minus 1 is plus 1. So by multiplying the corresponding contrast coefficients, we can form the interaction contrast. And we can see that what it amounts to is testing the null hypothesis that the difference between mu1 and mu2 equals the difference between mu3 and mu4, which is to say the difference between being primed and not being primed is the same whether viewed under difficult or under easy labyrinth conditions. That's exactly, of course, what it means to have an interaction effect. So, if you what it means not to have an interaction effect. If the difference between being primed and not being primed should be different under difficult and easy conditions, then of course we would have an interaction between priming and difficulty on the dependent variable. So I leave this for you to study when you look at the summary. If we order the contrast analysis as a follow-up analysis of a significant ANOVA F-test, this is what the output will show us. First of all, we get an overview of the contrast that we have actually ordered. And by looking at this table, once again, I can very quickly determine what sort of hypotheses have actually been tested over here. So looking at the various groups, difficult and prime, difficult and not prime, I can see that the first contrast tests for a difficulty effect, and the second contrast a priming effect, and the third contrast a interaction effect. Now, of course, if we test main effects, a main effect for priming, a main effect for difficulty, and an interaction effect, then the first what we will be looking at is, of course, the result of the interaction effect. Because if there is a significant interaction effect, then it may not be meaningful to look at the main effect by itself, but we might be more interested in looking at so-called simple effects, because once again, an interaction effect implies that the difficulty effect will be different under neutral and under perseverance primed conditions. And likewise, the priming effect will be different under easy labyrinth conditions in comparison to difficult labyrinth conditions. Okay, so the third contrast tests the interaction. So this is what I should be looking at first, and you can see here in the output, you have the opportunity to look both at the assumption of equal variances, so the case where the homogeneity of variance assumption is met, and we have another row where this particular assumption is not made. So if you have a violation of homogeneity of variance and you did the Welch test as an alternative to the ANOVA F-test, you can still do the contrast analyses and look at the lower row to see whether or not your effects were significant. In this case, we had homogeneous variances, so we can look at the first row. First thing we look at is the result of the interaction contrast. It's not significant. Now, in this particular case, we have orthogonal contrasts, which means that the contrasts that we have formed are statistically independent, and that means that we can immediately carry on with evaluating the main effects. So this is not significant, so we can now pursue our investigation of possible main effects, and we can see that both of these contrasts are in fact significant. So yes, there is a difficulty effect, and yes, there is also a timing effect, but they do not interact. Okay, so there are two possible strategies over here. You can do planned comparisons, so the contrast analyses, that is to say, if you have clear substantive questions that you want to ask your data, well, usually you will have such substantive questions, then you can form meaningful contrasts. Or alternatively, if you don't really have clear ideas about what sort of effects you're actually trying to seek in your data, you could also do all possible pairwise comparisons as follow-up. But we have seen, if you do all pairwise comparisons, well, there are 6 of these, and the unadjusted Bonferroni correction would be the significance level divided by 6. Now, if we have contrasts, as we have seen, there are only 3 meaningful planned comparisons corresponding to main effects and an interaction effect, and there was no Bonferroni correction necessary, because usually what we want to do is to keep the type 1 error probability at 5% for a given family of hypotheses. And families are usually each main effect that we want to test for constitutes a different family. So we will want to keep the alpha level at 5% for each individual main effect, and an interaction effect corresponds with another individual family. So for the interaction effect, we will also be wanting to keep our significance level at 5%. So in this particular case, if we do these 3 contrasts, we don't have to do any Bonferroni correction, because the 3 contrasts corresponds to 3 different families of hypotheses that we would be interested in. And therefore, planned comparisons or contrast analyses will have better power than doing simply all pairwise comparisons. Okay, Alberts and Martin, Alberts and his associates, obviously considered their design not as one way, but as a 2x2 factorial design. Because once again, we have 2 independent variables, difficulty and priming. And of course, they were interested in 3 families of hypotheses. First of all, the main effect for difficulty. Second, the main effect for priming. and third, the interaction effect. Each separate hypothesis was tested with an alpha level of 0.05. Now, we can see that the design was balanced or orthogonal. That's to say that in the experimental design, the independent variables were statistically independent from each other. You can see that the relative distribution of depleted is the same under not primed and under primed conditions. I should say that in the data file, difficulty is now suddenly coded as depleted versus non-depleted. This is exactly the same as what was first called not difficult or easy versus difficult. So do not come confused here. It is still the same, but in the data file, for some reason, it was coded as not depleted versus depleted instead of easy versus difficult. Okay, so we have two statistically independent experimental factors or independent variables, and we can do a two-way analysis of variance, which the output of which is shown over here. And what we see is that if we look at the upper row of this table, it says corrected model. That gives us the information of all effects taken together. And what you find over there, in the first row is exactly the same as what we found when we did the one-way analysis of variance. When we did the one-way analysis of variance, we were simply trying to see whether the four groups differ from each other. We did not truly distinguish difficulty, priming, and interaction. We simply had these four groups and tried to find out whether or not there were any, whether they differed or not. And the one-way analysis of variance that we did is in fact reproduced over here. So corrected model is are the results for all effects taken together, the two main effects and the interaction effect. Now here we have the results for the difficulty or depletion effect, and here we have the results for the main effect of priming, and here we have depletion times priming, that's the interaction effect. And if you look at the F values and corresponding P values over here, what you immediately observe is that the P values are similar to the ones we found just now when we did the contrast analyses, and the F values that we find over here are in fact the square of the T values that we found before when we did the contrast analysis. What this tells us, of course, is that when we do contrast analysis, we're actually performing a two-way analysis. Or, conversely, when we do a two-way analysis of variance, we're actually performing contrast analyses. There's not anything different going on behind the scenes. Here in the last column, we have a measure of effect size. In this case, it's called partial eta squared. And by convention, if you have a value of 0.01, you can say you have found a small effect. 0.06 would be a medium effect, and 0.14 would constitute a large effect. So what we find here is two main effects, which both can be designated as medium effect sizes. So we have actually found something interesting by uncovering the significant effects for difficulty and priming. Okay, here we see the difference between the means for the two difficulty or depletion groups. You can see that those who had the easy labyrinth on average had a difference between pre-test and post-test squeeze of about 4 seconds positive, whereas if you were faced with difficult labyrinths, you had a difference of about -8 seconds. So you can see that's a difference of about 12 seconds between these two groups on average, clearly showing that it does make a difference whether you first have to do the easy labyrinth or you have to do the difficult labyrinth. there was something like ego depletion going on, clearly. And here we have the priming variable, and we can see if you weren't primed to hold on, so if you had scrambled sentences about Nicole making tea, you have on average minus 7.5 seconds, so relatively bad performance. Whereas if you were primed to hold on, then the average of that group was about 3.5 seconds in the plus, so a relatively good performance. And you can see it's about 11-second difference between the two groups. Now, before moving on to the last part of this lecture, I'd like to ask, are there any questions so far? What I will do is, I will put the summary that I wrote of this lecture, I will put that on a layer this morning. And tonight and tomorrow night there are these voluntary tutorial groups. I want you to read through the summary again and to discuss these different former exam questions. And what I hope is that you get a certain grip on this material and a lot of questions you would like to know in addition, because I can ask you right now, are there any questions? But of course it all has to sink down a bit. It takes a little time. But if you look at these old exam questions, you will quickly start to have all sorts of questions that you would like to pose me, probably. And I hope that will mean that coming Wednesday in the afternoon we will have a very lively discussion on this same material when we do the practical lecture. Okay. Should I forget the summary, please give me an email and just remind me of it. You said you were going to post that summary this morning. I'll do that immediately. Okay, the last part of the first lecture is about unbalanced designs. We just had an example of an orthogonal two-way design. That is to say, the difficulty and the priming variables, the two experimental factors of our experiment, were statistically independent. Now here we have an example where we have two experimental factors, which I simply call A and B, where they are clearly not statistically independent. You can see that under the B1 condition, 43% of all participants had the A1 group, and 57% of all participants had the A2 group. However, in the B2 condition, 30% of all participants had a A1 group, and 70% had an A2 group. And lastly, in the B3 condition, 62.5% had a A1 group, and 37.5% had the A2 group. So you can see that these conditional distributions of the A groups is clearly different across the levels of the B groups. And that means that we're dealing with a so-called non-orthogonal design, or that our two experimental factors are statistically dependent. That is to say, they will describe the same variation in the dependent variable up to a certain extent, and we have to correct for that overlap. A and B are statistically associated. The effects of A and B can therefore not be unequivocally determined. We have to opt for a statistical correction in order to disentangle two effects. Because they are statistically dependent, they tend to become entangled, and we have to do something to make that undone. And that means that we have to opt for a particular computation of the variations, or the sums of squares, as they are called. Now here we can see in the upper table the situation where we've opted for so-called type 1 sums of squares, and here the more conventional or default type 3 sums of squares. If you order type 3 sums of squares, then the sums of squares that you will find in this particular column ascribed to the various effects, main effect A, main effect B, and the interaction effect, these sums of squares are unique. They do not overlap with each other. So the overlapping part is kept out of the analysis, so to speak. If you compute, on the other hand, type 1 sum of squares, then we are dealing with so-called hierarchical sums of squares. And this means, for instance, that the main effect of B is ascribed all the variation that A can in fact explain of the dependent variable. We do not correct any of the variation that can be ascribed to A. This is all the variation that can be ascribed to A. We do not correct anything. However, when computing the sum of squares, or the variation that we can ascribe to the main effect of B, we do correct for overlap with A. So A is given all the cake that it can be given, but B is only given that part of the variation that does not overlap with A. So it's corrected for overlap with A, but A is not corrected for overlap with B. Somehow we consider A to be more important than B. And the main effects are also not corrected for overlap with the interaction effect. Somehow we consider the main effects more important than the interaction effect. However, the variation that's ascribed to the interaction effect is corrected for overlap with the two main effects. And you can see that this particular value is the same as what you can see in the lower table, where the interaction effect where all the sums of squares are unique sum of squares. So this part of the sum of squares pertaining to the interaction effect does not overlap with A or B, and that's of course the same as what we should find over here, because A is not corrected for anything, B is only corrected for the main effect of A, but the interaction is corrected for both of the main effects, so that's truly unique. So this is a choice that we can make under some circumstances to compute hierarchical sum of squares, but default and usually the best option is to compute the unique sum of squares. Well, as you can see in both tables, the interaction effect is not significant, and if you have a non-orthogonal design where the various effects overlap, it's essential that you start with evaluating the interaction effects, and if they should not be significant, then they should be removed out of the model, and you should redo the analysis with every main effect included. And that's what we find in the second collection of tables, where the non-significant interaction effect has been taken out. And we can see that if you choose hierarchical sums of squares, that the effect of A is not significant, it's larger than 0.05. Effect of B is significant. However, if you choose the unique sum of squares, you can see that both effects are in fact significant. So it makes a difference what sort of particular statistical correction you want to opt for. Once again, usually it will be considered desirable to make use of unique sums of squares, so the so-called type 3 sum of squares. But there are some cases where a hierarchical computation of sums of squares should be preferred. For instance, let's say that A would be something like ethnic background, B would be level of education, then of course the computation of type 1 sums of squares would be more defensible than the computation of type 3 sums of squares, because A may have an effect on B, but it is impossible for B to have an effect on A. It's in the nature of things, so to speak. Okay, so this is what I wanted to tell you in the first lecture. It was mainly a review of bachelor material. I realized that for some people this was all very slow, and for some other people this was already a bit unnerving. But once again, I'm going to put the summary Anne this morning. I hope you will all attend the voluntary tutorial groups and that we will have a lively discussion on this topic. Hope to see you then.